Welcome back everyone to another video, and this time we're going to be covering second order linear homogeneous ODEs. So we already moved to the next chapter. We already left behind chapter 1, which was first orders ODEs, whether linear, non-linear. We saw the separation of the method of separation of variables and so on. And this time, this chapter, we're going to be covering second order ODEs. This topic is pretty straightforward. You can see the examples we're gonna be doing are gonna be pretty easy. So let's take a look as to how to solve these ones, and then let's do a few examples over the next few videos. So as you can see, we have here this time. This is how the second orders are identifiable, because we have now a y that has a double prime. If we didn't have this one, you can see it will be the same formula as when we had the first order ODEs that we just finished. But this time, because we do have a y with a double prime, this is how we know it's a second derivative, so it's a second order. You can see this one is homogeneous because all the non-zero terms have a y present, so it is a homogeneous term. Later on, we're gonna see the non-homogeneous, but let's focus for this ones with this ones for now. So in order to solve this one, it's pretty straightforward. The first step you always need to do is to write down your characteristic equation, and it will consist as the following. We're gonna have for every y that you have, or y prime, you will basically be putting a lambda. So for example, since we have a y prime, it will be corresponding to a lambda. If you have a y double prime, it will be a lambda square, and so on. And as we get to the next chapter, where we cover higher order ODEs, the method is exactly the same, and you'll see that we're just gonna keep increasing the power of that lambda. So to solve this one, you can see we basically write the equation in a characteristic equation. And if you see, this is nothing more than a quadratic equation. And you guys know how to solve quadratic equations. They're pretty straightforward. We have the quadratic formula. You can do factorization. Any method that you remember of to how to find the roots, it will be acceptable. So once we have the equations, we basically solve for the roots once again. And depending on how we get the roots, or depending on what the results for the roots are, we can have three different solutions. You can see that for case one, if we get our two roots to be real, meaning they are real numbers, whether they're positive or negative, and if they are distinct, or root 1 or lambda 1 and lambda 2, if they are both real numbers, not complex, real, whether positive or negative, and as long as they are different numbers from each other, this will be our solution. Y is equals to a constant 1 times e to the lambda 1x plus e2 times e to the lambda 2x. So once again, lambda 1, lambda 2, they can be positive numbers, negative numbers, doesn't matter as long as it can be different. So if we get, for example, negative 3 and 4, that's fine. That's a case 1. If we get a negative 3 and positive 3, well, that's still fine because negative 3 and positive 3 are two different numbers. Now, if we have case 2, in which we get that if lambda 1 is equal to lambda 2, then we get this solution. And in this case, lambda 1 and lambda 2 have to be the same number, both real numbers, but the same a quantity and sign. So 4 and 4, or negative 4 and negative 4, whatever. Both have to be the same sign and same magnitude. And if that's the case, you get C1 e to the lambda x plus C2 times x e to the lambda x. And you can see basically this one is just modified. Now, case 3 can have two situations. In case 3, basically you get it when your roots, they are complex. So if you get any imaginary plus real numbers, complex numbers, this will be its solution. You can see we have an exponential times the two trig terms, sine and cosine, where this beta is that real number from the roots that will go with the exponential, And then this omega that's in front of the I or behind the I will be that number that will be inside the cosine and the sine. And there's also the case for this case 3 that whenever you get pure imaginary, meaning that your beta is 0, you just get imaginary numbers like you see here, that exponential basically cancels out, because if beta is 0, then it's e to the 0 makes it a 1, and then you're just left with pure trig terms, sine and cosine. So once again, this method is pretty straightforward. We're going to do an example, and then over the next videos, we're going to get to solve them. And you can see these ones are examples that you can solve pretty easily. So let's get to it. Okay, so this is the first example. And you can see we have a homogeneous linear ODE with constant coefficients. And all that means is that our coefficients are going to be numbers. There will be the case where we might need to solve some equation like this, once again, where the coefficients are going to be functions, just as we have done in previous examples. But in this case, they're just numbers. And when that's the case, we use this method that we're going to be using for the characteristic equation. So we have the problem here, y double prime plus 6y prime plus 8 equals to 0. And they're asking us to find the general solution. So once again, let's solve this. So our first step should always be to write whatever our characteristic equation will be. And let's work it together. So we have y double prime, so that will correspond with a lambda square plus 6. You can see y prime, so that will be lambda plus 8y, and since that's just an ay, doesn't have a prime, so this should be plus 8, and it's equal to 0. Okay, so how do we solve this one? Well, we can use quadratic equation or factoring, whichever method you want to use, that's fine. In this case, we're gonna be factoring out. So what numbers will give me 8 and added up gives me 6. So when that's the case, let's see, we have 2 and 4. So we're gonna have our two parentheses here equal to 0. So we have lambda times lambda over here, and yeah, plus and plus, because all numbers are positive, and it's something that gives me 8 and also adds up to 6. So 2 times 4 adds 8, and 2 plus 4 does in fact give me 6. So that's that. So now let's solve for the roots. So we have then that lambda plus 2 is equal to 0. And therefore we have that lambda is equals to negative 2. And over here, we also have that lambda plus 4 is equal to 0. And therefore lambda is equals to negative 4. Now, whichever one you choose to be lambda 1 and lambda 2 doesn't really make a difference. You can choose whichever one. Doesn't make it wrong. So I'm just going to choose it like this. Lambda 1 will be equal to negative 2, and lambda 2 will be equal to negative 4. Now, if we remember what our solution was from our cases at the beginning, you can see that this is 2. We got 2 roots that are completely different. So this will, and both of them are real. So then we get that this is a case 1. And since it's a case 1, we get our solution should be in the form of y equals c1 e to the lambda 1x plus c2 e to the lambda 2x. That will be our form for our solution. So let me write my general solution here. And we're going to get then that y of x, it's equal to c1 e to the negative 2x plus c2 e to the negative 4x. And this, ladies and gentlemen, is our general solution for this problem. You can see that it is pretty straightforward. It's nothing complicated at all. It's pretty easy to find, doesn't take too long, and it's one of those problems that can be solved pretty easily. So we're gonna do another one. You can see in this case, this is a general solution because our C1 and C2, they're not solved. We don't know what they are, but once we're giving initial conditions, we can find out whatever they are. So that's it for this one. I'll see you in the next video.